land conference and worldbank.org,
Excellent.
and just as a backup. Yeah,
Very good. Thank you.
thanks.
Hello.
Ms. Zhang, I can confirm with you now that we can see your share. So that's wonderful. You'll just want to
So you can see my slides.
I can see them right now. Yes, you're sharing them.
Okay.
So you can stop that share until you go to present later this afternoon.
Okay.
Thank you.
Good afternoon. Thanks, welcome for joining. We have another important session. I think many sessions have been had already. So there will be 4 papers presented in this session, which is entitled Land Markets, Migration and Structural Change. I suggest we start in the order of the program, follow the order of the program. So the first one will be on structural change by Budi-Ors, or rather Thomas Budi-Ors, who is a research economist at the Bank of Spain, and reading from the abstract is quite intriguing and provocative findings, so we're looking forward to hear his presentation. Thank you.
Thank you. Thank you, Luca. So thank you everyone for coming. This is maybe not directly related to land, but perhaps indirectly. I will let you judge. So as you all know, macroeconomic development is not only defined by a sustained increase in income per capita, but also by major reallocations of production factors. So in the case of labor, we know that as countries grow, employment shifts from agriculture to non-agriculture, as we can see on this picture on your left, that plots the agricultural share of employment against GDP per capita for a large sample of countries, and that simultaneously people move from rural to urban areas, which is this picture on the right that plots the urban share of employment against GDP per capita for the same sample of countries. These two aggregate reallocation processes, structural change and urbanization, are typically studied jointly in the macroeconomic literature, making the assumption, most of the times implicit, that rural areas are equivalent to the agricultural sector and urban areas to the non-agricultural sector. Under this assumption, it follows that spatial frictions that prevent spatial frictions actually prevent structural change and hence may have a large impact on economic development, to the extent that we think that moving workers out of agriculture has a large impact on value added per worker. So what I'm going to do in this paper essentially is to take a step back and explicitly differentiate between the reallocation across sectors from the reallocation across locations. I'm going to study the forces and frictions that are going to shape each process and the relationship. And then with the model, I'm going to look at the macroeconomic implications of this, let's say, this differentiation. I'm going to do that using data from Indonesia, which by no means it's an exception in the reallocation of labor out of agriculture and from rural to urban areas as the country has been growing, as you can see on the orange dots here. More specifically, what I'm going to do in this paper is that I'm going to use a long-run individual level panel data for Indonesia. And I'm first going to show that workers switch from agriculture to non-agriculture within rural areas. This is, they do not migrate from rural to urban areas in order to leave the agricultural sector. Instead, rural-urban migrants are individuals who already work in the non-agricultural sector before moving to cities. Next, I'm going to show that the aggregate reallocation out of agriculture, this is the fall in the agricultural share over time, it's going to be mainly driven by young cohorts entering the labor market directly in the non-agricultural sector and hence pushing down the aggregate agricultural share. Thirdly, I'll show that despite rural-urban migration does not imply a change in the sector of occupation for migrants. Remember, fact one. It seems to have an effect on the sector of occupation of the next generation. In particular, I'm going to show that the offspring of rural-urban migrants are going to be much more likely to work in the non-agricultural sector than the offspring of comparable rural stayers. With these facts in mind, I'm going to build a quantitative model of two locations, rural and urban, that are going to have two sectors each, an agricultural and a non-agricultural sector. And that is going to be populated, these two locations, by overlapping generations of agents that are going to differ in their initial conditions when they join the labor market in terms of locations, or in which location they're going to be, and also in terms of human capital. And that are going to choose every period in which location, sector they want to work, taking into account that moving across sectors and moving across locations is going to be costly. So there are going to be both sectoral switching costs and spatial frictions. And also that their location choice is going to have an impact on their offspring. In the model, structural transformation and urbanization are going to be mainly driven by asymmetric productivity growth across locations and sectors, kind of in a standard neoclassical multi-sector growth model. I'm going to calibrate this model to match these employment reallocation patterns I've documented for Indonesia, and also the growth in output per capita between 1983 and 2013 in this 40-year period. And then, armed with the model, I'm going to run a few counterfactual exercises. The first counterfactual exercise I'm going to run is I'm going to simulate an economy in which migration is not possible. And what we're going to see in this economy is that the agricultural share is going to fall by almost as much as in the economy with migration. Hence, that's what I'm saying here, that rural-urban migration is going to have a very limited impact on a structural transformation or a structural change out of agriculture. The reason is that the non-agricultural sector is going to manage to develop in rural areas because its productivity growth in the non-agricultural sector in rural areas is going to be able to absorb labor. However, the economy is going to grow less because the non-agricultural sector is less productive in rural than in urban areas. Next, I'll show that the main reason why different cohorts of workers have very different agricultural shares over their working life is not that much their initial conditions, the fact that young workers are more educated than older workers, but actually that once you enter a sector, once you enter into agriculture, it's very difficult to leave. So these sectoral switching costs are going to be very important in the allocations of different cohorts. These two findings together, so the fact that rural-urban migration, so is not so important for structural change, and the importance of sectoral switching cost, lead me to sort of conclude that spatial frictions may not be so important for structural transformation as previously thought. Okay, so now let me go in more detail to the facts. Very briefly, the data I'm using mainly is this Indonesian Family Life Survey, which is a panel survey of Indonesian households. Maybe some of you here have used this data set. It's a well-known data set. Has 5 waves, first one 1993, last one 2014, more or less every 5 years. best two things of this data set for this question I'm after. There's very little attrition. So when an individual migrates, you typically don't lose it. And second, split off households from the original sample households are typically followed, which allows for this intergenerational analysis. Okay, so from now on, I'm gonna talk about, I'm gonna classify workers in 4 location sector categories: rural agriculture, rural non-agriculture, urban ag, urban non-ag. And first thing I'm gonna show is what happened with these 4 categories as a share of total employment in Indonesia over this period of time. And what you can see is kind of what my initial motivation pointed at. So the share of employment in the rural agricultural sector falls while simultaneously the share of employment in the urban non-agricultural sector increases, which might lead you to think, okay, farmers are moving from the rural agricultural sector to take non-agricultural jobs in the city. However, when you look at the microdata, you discover that there's some relevant and interesting micro-heterogeneity. So what I'm gonna do now is just looking at what's the probability that you move across from one sector to another at the individual level using this panel data, so the fact that we can see workers for several periods of time. I'm gonna record these movements in this transition probability matrix. The first thing I wanna highlight in this matrix is that the movement from the rural agricultural sector to the urban non-agricultural sector is indeed quite small. It's the flow from rural agriculture to urban non-agriculture is only around 3% of all the rural agricultural workers every 5 years do this type of move. Instead, it is much more common to leave agriculture within location. So almost 20% of workers, of rural agricultural workers, leave agriculture in their same location. Then who are the migrants? So migrants, as you will see here, are mainly workers who already work in the non-agricultural sector in rural areas and that move to the non-agricultural sector in urban areas. These 13 percentage points that you can see here from rural non-agriculture to urban non-agriculture. Also importantly, just let me highlight that you get the standard finding in this literature that moving from agriculture to non-agriculture or moving from rural to urban areas is typically associated with large gains in individual income, which might be suggestive of the presence of frictions to do both movements. And indeed, the workers who, the few who move from the rural agricultural sector to the urban non-agricultural sector get a large earnings premium. So this first fact is about the movement of individual workers, but we know that the agricultural share might fall over time, the aggregate agricultural share, because yes, these individual workers move, these individual workers that belong to different cohorts leave agriculture over the working life, but also because new cohorts are gonna join the labor market, old cohorts are gonna retire, and they may have different agricultural shares. And this is essentially what you can see in this picture. So at any point in time, you can see that lighter blue dots have a lower value, so younger cohorts at any point in time have a lower agricultural share than older cohorts, and that the cohort level agricultural share, its evolution is much flatter than the aggregate agricultural share. You can put this in numbers. Actually, it's more like 60 to 70. There's a typo there of the reallocation can be attributed to cohort effects. So the last fact, so I showed you that at the individual level, rural-urban migration doesn't imply moving out of agriculture, that at the aggregate level, these new cohorts seem to matter for structural transformation. Finally, I'm sort of going to connect these two facts. What I'm gonna do is I'm gonna compare the offspring of rural-urban migrants to the offspring of rural stayers. So essentially, it's a regression in which I compare outcomes of the kids, and I have this rural-urban migrant offspring indicator. And what I'm gonna show is that the offspring of rural-urban migrants have higher educational attainment, a lower probability of working in agriculture, even conditional on their educational attainment, and also higher earnings. And these are all these facts are gonna hold true conditional on parents' sector, parents' education, and also even parents' unobservable characteristics as captured by a fixed effect that you can get from a parent level regression and put it as a control in the kids regression, which is what I'm calling here, maybe a bit of an abuse of the word, but an intergenerational return to rural-urban migration. So let me quickly go to the model. So with these three facts in mind, how individuals move, how the aggregates depend also on these changes in the composition of the labor force, and finally on these intergenerational linkages, have this model that there are going to be two locations, a rural and urban location, and two sectors, an agricultural and a non-agricultural sector. In each sector, there's going to be a final good. There's going to be a composite of intermediate varieties. These sectoral intermediate varieties are going to be produced in each location with location-specific productivity. So the urban non-agricultural sector is going to have a different TFP than the rural non-agricultural sector, for instance. And combining high and low skilled labor also with different intensity in each sector. So the urban non-agricultural sector is going to be more skill intensive than the rural non-agricultural sector, for instance. And obviously, non-agriculture is going to be more skill intensive than agriculture. And then these varieties are going to be tradable across locations subject to some trade costs. These two locations are also going to differ in the access to education they provide to the residents. The residents are, as I hinted at the beginning, overlapping generations of agents that are going to live a life cycle of 60 years. So for the first 20 years, they are going to be just children. The only thing they are going to do in the model is acquire education in the location of their parents. Then at age 20, they are going to become high or low skilled agents. With probability P, they will become high skilled agents, and this probability is going to depend on the location where they have been raised, and actually also on the investment that their parents making them. Once they become high or low skilled, they are going to join the labor market, and every adult period, they are going to choose in which location and sector they want to work, taking into account that switching across location sectors is going to be costly. And this is going to introduce dynamics because agents are going to consider that if they enter agriculture today and in the future, the aggregate conditions might change, they want to leave agriculture, they will have to pay a cost. So they will anticipate this. And also they will anticipate that if they go to the city, their kids are going to have different opportunities than if they stay in rural areas. Once in a location sector, in a period, they are going to consume both the agricultural and the non-agricultural good, and this is going to be determined how much they consume by these non-homothetic preferences that are standard in the structural transformation literature. So I sort of describe the model quickly. You have like this, let's say the production side of the economy and then the consumption and labor supply side. So at every point in time, the labor supply in the model is going to be these agents taking this, solving this dynamic location sector choice problem, which depends on the switching cost. And the labor demand in each location is going to be mainly determined by productivity. In the model, structural change will be generated mainly by asymmetric productivity growth. And importantly, the fact why different cohorts might have different occupational employment shares is because, well, when I'm young and I join the labor market, I don't pay a switching cost because I'm not switching from any sector. Second, young workers may be more educated than old workers. And lastly, and this is particularly new, which is these dynamic effects of rural-urban migration. The fact that by moving to the city, workers are generating the future labor supply, the future educated labor supply. Okay. So, I mean, I'm going to calibrate the model by a standard simulated method of moments. Let me go very quickly over this and talk about the counterfactuals and the results. So the first counterfactual I'm going to do is, as I said at the beginning, I'm going to stop rural-urban migration. I have an economy in which workers cannot migrate. So this is the evolution of the agricultural share in the benchmark economy, so in the migration in which workers do migrate. And this is the evolution of the agricultural share in the economy without migration. And as you can see here, it's actually very, very similar. What's happening? It's what I call here rural structural transformation. So I want you to focus on the two graphs on the column on your right. And as you can see here, in the benchmark economy, the rural non-agricultural sector is more or less flat. But when workers cannot migrate, the rural non-agricultural sector as a share of the total labor force grows quite a lot, compensating almost entirely for the fact that the urban non-agricultural sector cannot grow as much as this economy. Look at the lines are sort of the mirror of each other. The reason is that the rural non-agricultural sector, productivity grows there, and hence actually workers are pushed to that sector in rural areas. However, this is going to come at the expense of economic growth, which at every point in time is lower output per worker in this economy, because the non-agricultural sector is less productive in rural areas, which is something that I guess doesn't come at a surprise. Second, this is the agricultural share of each cohort in the benchmark economy. Remember that different cohorts may have different agricultural share for mainly two reasons. One is that they have their different initial conditions, so they are different. I'm young, I might be more educated than some older people, and that's more valuable outside agriculture. But also because older workers are already in the agricultural sector, and if they want to leave, they have to pay a cost. So I'm going to sort of try to quantify these two mechanisms. And look, in an economy in which workers can freely live or freely move across sectors, the differences in the agricultural share across cohorts essentially disappear. So you can see here that in 1993, for instance, the difference between the youngest and the oldest cohorts is 20 percentage points. That almost goes away completely when workers can move freely across sectors. Instead, when education is equally valuable across sectors, while you get some, it shrinks the difference, but it's not nearly as strong. So to conclude, structural change and urbanization, as you know, are two defining features of economic development. I think using individual level panel data from Indonesia, I've shown that perhaps the picture is a bit more complicated than previously thought. And I think it matters that the fact that the picture is a bit more nuanced, it matters because what this reveals is that frictions to change sector and not so much spatial frictions seem to be the main impediment for a structural change, defined as the reallocation of employment out of agriculture. What do these sectoral switching costs reflect? Well, it might be that there are something related to human capital that might be sector specific, but also might reflect stuff like frictions in land markets. And actually I show, I'm not gonna click in the interest of time, that workers who leave the agricultural sector in rural areas own less land and are typically work more for other people than working by themselves, saying that it might be difficult maybe to sell land, or it might be difficult to sell land, particularly if you work on your own farm, which is, I think, more related to the things we have been talking these days. Okay, thank you. We do questions now, or
yes.
as you want? Okay.
Thanks a lot. Fascinating presentation and provocative insights. So open for questions.
Thank you, Thomas, for that fantastic paper. So one question I had was, how do you separately identify the spatial from the sectoral frictions, these switching costs that you talk about? And the second is, how do you identify the productivity in the non-agricultural sector in the rural economy? Because that seems to be very important for this result, that if you shut down rural to urban, the productivity has to be high enough to absorb everybody that is going to stay. So how do you identify
Yeah, so the main two pieces of data that I use to identify this are so the flows across location sectors, so the transition matrix, and the differences in wages across location sectors. So in this case, say you observe a lot of people moving from one sector to the other, and you still observe a very high wage difference between these two. So you are gonna, in that case, I think, recover a high productivity of that sector relative to the rest, and also a high friction that is preventing actually the equalization of incomes across these sectors. Essentially, yeah, it's using both kind of prices and quantities, so the flows and the relative wages across these four groups of these four location sectors. Yeah, let me maybe elaborate. So, okay, I have it somewhere. So, okay, well, I have too many things here. Okay. So, as I highlight here, so productivity is gonna map to the value of a given location sector. Essentially, it's gonna, if you increase the productivity of a location sector, it's gonna increase the relative wage of that location sector, all else equal. This is gonna attract workers from all location sectors in principle. However, you do not observe workers from all location sectors coming at the same rate, and this is essentially gonna be controlled by the costs. And then with this, let's say 4x4 matrix, and then the relative wage across these groups is what's gonna recover both the relative productivities and the costs.
I was wondering if you consider the role of remittances and household dynamics, like possibly if a household has two sons, one son migrates, sends money back, and that allows the other son to switch from agriculture to non-agriculture within the village, for example. So that was my first question. And the second was thinking about generalizability of the result. Like, is there something specific to the Indonesian context that leads to this growth of the non-agricultural sector? Or do you think it would apply to other developing countries as well? Thanks.
Yeah.
Thank you very much. Indonesia is a very unique country. Java, densely populated. Kalimantan, very few people. And you said the rural areas in Java, in rural areas there are agriculture and non-agriculture. But if we go to Kalimantan, rural area is agriculture. and I'm curious about the future of Indonesia. Lots of people migrate to Java, or some people not really transmigrate. But also I'm curious about the quality of schooling in Java versus Kalimantan or Sumatra, Sulawesi, so on. I think it's interesting to see apply this kind of model to Java and other areas and see the future of Indonesia.
Okay, so to your first question on household dynamics, so not really, I haven't considered that. It's so I think it's interesting. I have spent some time thinking about how like in these models, typically we think of a unitary household, and it might be interesting to extend it to actually like think carefully about this stuff. I haven't done it. The only thing I can tell you is, well, I think first that I think Tasso has a paper with more interesting households, and also that what I looked at is that. First, the transition matrix look very different. Look very similar by gender, and second, there's a very high correlation between the household head moving and the wife moving out of agriculture. So they do typically this at the same time. But yeah, I haven't explored much more. And then the second question is similar to his on the general. How general is this? So I think that in the context of Indonesia, it's true that but that in Java, like there is a lot of peri-urban areas or rural areas that are maybe slightly bigger than what we typically think of a rural area. and in that sense, I see that there is a point in to what extent this is very general. I haven't explored the heterogeneity by islands, so the data here mainly is about Java and Sumatra. So there's not that much about other islands. So yeah, still, let me just to conclude say that these are still rural areas in the sense that these are not cities. So something I observe is that the average place where these farmers live agriculture has around 3,000 people, the municipality. So it's actually, it's a village. Then obviously, there are concerns, I agree, but it's not that I'm mislabeling rural areas, I think. I have done some robustness on that, and yeah.
In the interest of time, I suggest we move to the next one. So if that's okay, Klaus, and the chair. So okay, then I suggest we move to the next one. So next presentation will be, thank you. Will be more squarely land and land rental and different land rental agreements and how that affects investment in soils. So this will be presented by Dr. Dan Zhang, a postdoctoral researcher at the College of Economics and Management at Nanjing Agricultural University in China. Go ahead. Thank you.
Hi, can you see my slides?
Yes.
Okay. Good afternoon, everyone. I'm so sorry that I cannot be there in person today. And a huge thank you to the organizer give me such an opportunity to present online. And the paper I want to present today is Land Rental, Soil Health, and Land Investment Differences. Panel survey evidence from rural China. Healthy soil is important for food security and sustainable agricultural development. However, soil degradation remains a serious global challenge. Around 1/3 of the world's farmland is gradually degrading over time. This makes soil conservation not only an environmental issue, but also an important issue for agriculture productivity and long-term food security. A range of soil conservation farming practices, we call them CFPS, they have been shown to promote soil health. However, a key feature of many soil conservation practices is that their benefits are often delayed, which means that farmers may need to bear the cost today, while the gains may only appear in future production seasons. This creates an important economic question. If a farmer is not sure whether he or she can continue cultivating a plot in the future, will that farmer still be willing to invest in those practices? This is where land tenure security becomes central. Now, there is a large literature on secure property rights and agricultural investment. However, empirical findings are mixed. Some studies find a positive relationship, while others find weak or insignificant effects. And some literature suggests that the relationship may depend on the type of investment, local institutions, and so on. And China provides an important context for studying this issue. First, China's farmland system is based on collective ownership. farmers do not privately own farmlands, but they can transfer their management rights through the land rental market. This institution setting creates a distinction between farmers own contracted land and rented in land. Second, soil degradation has become an increasingly important concern in China. For example, some studies found that black soil will be completely eroded in 130 years. Third, China's farmland rental market has expanded rapidly, and now farmland transfer accounted for about 34% of total household contracted farmland area. Given the scale of rented farmland, if land rental weakens farmers' incentives to promote soil quality, the implications could be substantial. So our study contributes to the literature in three main ways. First, many existing studies use aggregated level soil data, such as county level. These studies are useful for understanding broad patterns of soil degradation, but they cannot fully capture differences in land tenure across plots, especially within the same household. Second, some studies compare landlords and tenants, but these comparisons may suffer from endogeneity, since landowners and tenants may differ in many unobservable ways. And our study addresses this issue by comparing old and rented-in plots operated by the same households in the same year. Third, many studies on China focus mainly on organic fertilizer. However, soil conservation investment is broader than that. And in this paper, we examine several soil conservation practices. And based on what I mentioned before, in China, farmers do not hold the land privately. They only have the contractual rights and management rights, but they can transfer their management rights to others. So in rural China, farmland transfer often occurs through social networks. Many land rental transactions take place between relatives, neighbors, or acquaintances. And these transactions are usually private, and farmers prefer oral contracts than written contracts. But generally, written contracts can specify the rental parties, payment methods, and so on. But oral contracts may be less observable and less enforceable. This may make tenants less confident that they can continue cultivating the rented plots long enough to benefit from long-term soil investment. So, from the perspective of tenure security, farmers' own contractual land is generally more secure than rented-in land. And among rented-in land, land obtained through a more formal market is generally more secure than those obtained from acquaintance markets. And in our study, we focus on 4 CFPS and 2 non-CFPS. And comparing to non-CFPS, CFPS benefits usually take time to be realized and is limited by factors such as machinery and capital, which means the use cost is high. We have three hypotheses. First, the soil quality of rented-in land is lower than that of farmers' own land. Second, overall, farmers are more likely to adopt CFPS on their own land compared to rented-in land. Third, farmers are more likely to adopt CFPS on rented-in land with more formal land rental contracts than on rented-in land with less formal contracts, because such formalization can boost the talent farmers' sense of land tenure security. And we used 2 rounds of household survey conducted in 2015 and 2018 from 4 major grain producing provinces in China. And the survey covered 4 provinces, 4 cities, and 2 towns in each city. The total number of households was 1040 in 2015 and 1033 in 2018, and the follow-up rate is 82%. We also examined whether sample attrition may bias the analysis, but the results suggest that attrition is unlikely to induce systematic bias into our estimates. And for each household, the survey collected plot level information on farmers' owned and rented-in land. And in general, the survey focused on the largest owned plot and largest rented-in plot under the same crop, which is useful for comparing plots within the same household. But the soil testing only for large-scale households. So the final sample includes 530 observations in 2015 and 330 observations in 2018. And here are our empirical strategies. To test the first hypothesis, we compared the soil quality indicators between farmers' owned and rented-in plots. The soil quality indicators include pH, organic matter, nitrogen, phosphorus, and the potassium contents. And to test the hypothesis two, we compare farmers' adoption of different soil conservation practices on owned and rented-in plots. And these practices include deep tillage, no tillage, crop residue retention, and organic fertilizer application. And we also examine non-safety inputs such as chemical fertilizer and pesticide use. And to test the third hypothesis, we focus on rented-in plots and compare plots with different forms of rental contracts. We distinguish between oral and written contracts and registered and non-registered contracts. And the first set of results examines the land rental and the soil quality. The results show that the soil quality on the rented plots is slightly poor compared to old plots. And the rented-in plots have lower phosphorus content and are less likely to have pH values within the range suitable for crop growth. But the differences in organic matter, nitrogen, and potassium potassium are not statistically significant. But there is a potential concern because because these differences may simply reflect initial quality differences. In other words, farmers may rent in plots that were already of lower quality before the rental transaction. We address this concern in several ways. First, we control for observable plot characteristics, such as the plot size, distance, flatness, and so on. Second, as previous studies have shown, plots that are close to each other usually have very similar soil quality. So we narrowed our sample down to owned and rented plots that are geographically close, especially the plots within 150 meters of each other, and even those right next to door. And the results seem remains consistent with our main findings. We also conduct descriptive comparisons. First, we compare landlord's owned and rented out plots, and we find that except for flatness, there are no significant differences in characteristics between rented out plots and owned plots. We also examine self-reported soil quality of rented-in plots over time. And although this is a subjective variables, but we find that these measures still has a certain degree of validity. As this table shows that the farmer's self-reported soil quality is positively associated with objective soil indicators such as the organic matter content and the phosphorus content. So, and this then this and this result examines whether farmers invest differently in owned and rented-in plots. We find that farmers are less likely to adopt certain soil conservation practices on rented-in plots. In particularly, compared to owned plots, rented-in plots are less likely to receive deep tillage and organic fertilizers. But for no tillage and crop residue retention, we do not find statistically significant differences. And we also examined the use of non-CFPS inputs. The results shows that compared with old plots, farmers tend to apply more chemical fertilizers and pesticides. And these results focus on whether more formal rental arrangements can mitigate the negative relationship between land rental and the soil conservation investment. And we find that farmers have the lowest willingness to adopt some soil conservation practice on rented-in plots with oral contracts or non-registered contracts. And in further analysis, we focus only on farmers rented-in plots. We find that written contracts are positively associated with land investment. And there are three main takeaways. Soil quality is somewhat lower on rented-in plots than owned plots. farmers are more likely to adopt certain CFPS on their own land and apply chemical fertilizer and pesticide on their rented-in plots. The negative relationship between land rental and farmer investment in CFPS is mitigated by improved land tenure through better contractual arrangements. However, this study also has several limitations. First, the panel covers only 2 survey rounds. Some soil conservation investments may take longer to affect soil quality. So a longer panel would allow us to better capture dynamic effects. And second, the soil testing only focus on large-scale farmers. Although this group is important in China's agriculture transformation, but in many developing countries, small-scale farmers still dominate the agricultural production. So the external validity of these findings should be interpreted carefully. Third, analysis is limited to soil conservation and non-conservation practices observed in the survey. Further research could examine a broader range of land management practices. And that's all. Thank you for your listening.
Thanks a lot. Another round of fascinating findings. Opening the floor for questions.
So the quality of rented-in land is lower. That's a major conclusion of your study. So that means those farmers who rented in do not take care of soil very well. So my question is, who are renting out the land? Are they farmers or are they migrants to cities so that they cannot monitor? Because in other Asian countries, I don't think this kind of thing happens. Usually the tenancy contract, yours is not tenancy, but tenancy contract is a long-term contract. And the farmer, the landlord and tenants are really close friends, sometimes father and son. And there is a trust among them. So this kind of thing does not happen. So either land right security is not very high, or those who rent out the land has gone and then working in cities so that they cannot monitor anything about farmers who rent in the land. So what is happening there?
Let's maybe take a couple of questions. Let's take a couple of questions.
Okay, you look at a larger farmer in China, own land is normally only 0.3, 0.4 hectare, 0.5 hectare. And then you have larger farmer, if 10, 20 hectare. So own land is small one, and the renting is bigger one. And own land maybe for produce for own consumption. So they use organic or some other. The larger land is normal land, and so you also mentioned limitation. You focus on larger farm. I think you are right in that limitation, because own land it's so small and renting land is so big. It's not compatible. Did I get clear?
All right. Do you want to respond?
Yeah, and the first question is that now in China, some small farmers will rent out their plots, but they will still own some plots. For example, they may rent out the plots which is very far from their house, and yes, some farmers may rent all of his plots and active the agricultural sector. And the large-scale farmers in our study actually is not very large, and the average plot size in our sample is less than 1 hectare. And the rented-in plots is bigger than 1 hectare, and the farmers' own plots is less than 1 hectare.
Yeah, I think your discussions are interesting, and those points should be incorporated into your estimation equation.
Any other questions?
Thanks for the presentation. I was wondering if you have data on, I guess, like how long the person has been renting that piece of land, especially because you were saying that a lot of the rentals are through relationships, and if you can sustain the relationship, then maybe you would see more investment in the land. And so I wonder if you can do that heterogeneity in your data.
Yeah, we do have that information about the duration of farmers all these rented-in plots. And yeah, thank you for your comments. I will do that test later.
Yeah, that seems like an obvious extension. One other just remark I made to myself on the results. Maybe the fact that those who rent tend to use more chemical fertilizer. Those who own tend to invest a little bit more in soil conservation practices. If you put the two together, that may be a reason why you may not see in a number of studies so much effect of land tenure security on investment, on higher yields, etc. Because in this case, in the short run, chemical fertilizer and investment in soil conservation practices could act like substitutes. And it's just a thought which occurred when you put the two together. So the null results, if you want, which you highlighted at the beginning from your literature review, where there were many with insignificant results, maybe because you could get a bit of these counteracting effects. And anyway, it's just a thought.
Thank you.
If there are no other questions, then I suggest we go to the next presentation. Thanks a lot. So the next presentation, we're switching gear. We're switching gear a little bit again. We're now bringing in the environment and looking more at environmental enforcement or enforcement of environmental measures and how that affects deforestation, how it affects land management, if you want. So it's all about land, but at different angles. This will be a presentation by Marie-Louise Descamps, an economist at the World Bank in the Development Impact Group. Fire away.
Thank you so much. Hi, everyone. Thanks all for being here on the last session. Good to see the room be full. So yes, today, now we're switching gears a little bit and I'm going to talk to you about a very preliminary project about state capacity and environmental protection. So any question and feedback are very much appreciated. Oh, and this is with my colleague Davis Desed, who is at Bocconi. So it's probably a well-known fact that forest conservation is a public good. So on one side, deforestation is a really large contributor to greenhouse gas emissions. We're estimated between 8 to 20% of global greenhouse gases. It is a biodiversity hotspot, and it also helps with climate regulation through these flying rivers. However, forest conservation is very challenging, despite it having all these very positive benefits, mainly because deforestation brings a lot of economic benefits for farmers, especially. I mean, 90% of tropical deforestation is driven by agricultural land expansion, and so this is a classic case of private benefits not equaling social benefits. And another complicating factor is that environmental violations occur over a really large area. If you think of, the Amazon, it's just a really large space, and kind of monitoring and enforcing regulation across these very remote territories is very difficult. And especially because tropical forests are usually located in low and middle income countries that might have a limited state capacity to enforce this regulation. On the detection side, satellite monitoring technologies have improved the ability to detect violations across these very vast territories, but enforcement still often relies on acting on that information and having people to go out and really act on the detection. In this paper, the question that we want to answer is, what is the impact of weakening local enforcement resources for environmental protection? We're going to study this question in the context of Brazil by looking at the federal environmental agency called IBAMA. And we're going to study this over a period of 2014 to 2024, where there was a really large reduction in enforcement capacity that coincided with an increase in deforestation. So due to several reasons, which I'll go into later, there was a 28% decline in staff, and that led to the closure of about 45% of field offices nationally. So in this figure on your right, you see that the dots are all the office locations, and the ones in red are all the ones that closed. And we're going to combine this kind of natural experiment with very rich administrative and satellite data on detection, enforcement, and land use. We speak to two broad sets of literatures. So the first is in the really large literature thinking about what are the drivers of deforestation and what policies favor conservation over deforestation. And I think what we're adding to this literature is studying a reform to the main bureaucracy that's tasked with implementing these conservation policies. So what happens when you have policies, but the capacity to implement them is weakened? And then second is the literature on public sector personnel, in particular related to the study of environmental agencies. And here we're going to look at the role of state capacity in forest conservation, which to our knowledge hasn't been as explored, and also how the personnel interacts with satellite monitoring technology and the complementarities, or whether they're complements or substitutes. So for today, as I mentioned, we are still at some preliminary stages. So next I'll go into the context and the data. I'll then show you impacts on agent presence, and then I'll close with the impacts of the office closures on enforcement. So for some background, this is the trend of deforestation in Brazil between 2010 and 2024. There are about 300,000 square kilometers of forest loss. And while from 2004 to 2012, there were a lot of pro-environmental policies, including the introduction of satellite monitoring technology. Since 2012, there's kind of been a reversal in the trend with deforestation picking back up. So the main drivers of deforestation in the Amazon is cattle ranching, expansion of cattle ranching, and agriculture. There's also some smaller scale deforestation for mining and logging, but really you should think about who's doing this deforestation. It's really cattle ranchers expanding their land. And deforestation is largely illegal in this context. So in public and non-designated land, it's always illegal. While on private land, there are some requirements of having these, protected areas. So you could deforest in your private property up to 80% of the land. And if you do that, it still has to be authorized by IBAMA. However, despite deforestation being illegal, weak property rights facilitate land grabbing and deforestation. So, for example, the Cadastro Ambiental Rural, CAR, is the environmental registry of properties, and it is self-declared. And there's some evidence that this has been exploited to really claim land illegally on these public areas where deforestation is illegal. So there's a large role for enforcement in this setting. And the agency in Brazil tasked with doing this enforcement is IBAMA. It's organized into headquarters, which are in the state capitals, and a set of field offices, which are in 2013, there were 110 field offices spread across Brazil. Here on the right, I'm showing you the three types of offices, so the regional headquarters and the national headquarters, which are in Brasilia, the country's capital. And then in the orange color, you see the share of agents in field offices. And you see that these field offices are a pretty small share of total agent presence, but I'll show you that they still play a significant role in enforcement. And their relationship with the regional headquarters, you should think, the regional headquarters have the coordinating capacity of coordinating enforcement activities across their states, and then field offices being responsible for implementing these, the enforcement. As I mentioned, Brazil is a context where there is satellite monitoring detection, and so when you're thinking about how is IBAMA finding out about where illegal activity is happening? Well, it has both the TER system, which is the satellite monitoring, and also these field offices also play a role in gathering local knowledge about what's happening on the ground. So here on the right, I'm showing you the map of the legal Amazon, which is where this paper is going to be focusing on. The orange dots are the offices, and then the shaded areas are kind of places that had deforestation alerts in 2014. And so you see that there's also kind of a mismatch between where alerts are happening and where offices are. And so we can use this to think about also the how should be the optimal distribution of local offices. Does it make sense to have them decentralized, or would it be better to have the centralized and then deployment of agents across space to respond to these alerts? What happens if you're caught? Well, there are several types of consequences. The most common one is to receive a fine, but fines can be accompanied by more severe enforcement, such as embargoes, which basically means you cannot produce on your land anymore, seizures of equipment that, for example, was used to do the deforestation, and suspension of activities. And how enforcement happened in practice? So both field offices play an important role in enforcement because of the agent present on the ground, but there are not offices everywhere, and so sometimes there are these mobile operations that are really able to travel to on-site to translate the detection from the system to enforcement. It's also possible to automatically enforce alerts when you're able to overlay them with the registry of properties, because you're able to identify who that property owner is. And so we actually see that about 48% of deforestation fines are enforced by mail. And so you think that when registries are better, you don't necessarily might need to have this field offices, and we'll try to do some heterogeneity. You'll see later by that. So what happened to state capacity in this context? Between 2013 and 2016, there was a really large decrease in the budget for IBAMA of about 40%. And this translated to an overall decline in staff of 22% between 2014 and 2024. And that was concentrated in the legal Amazon, where there was a decline of almost 29%. This decline in staff led to the shutdown of offices and a shift from local offices to mobile deployment. And so here I'm showing you a graph where we compare offices that were never closed in light blue. We see that they always have an agent present. In yellow, offices that will be closed but are still open, they they're almost always staffed. And then those that are closed, there's a really large decline in number of days with staff. And so this shows that there was a really large decline in presence that became more intermittent and not permanent present throughout the year. Why were there, what were the explanations for doing all these office closures? Well, there were budget cuts, but another argument that was being used is exactly this flexibility in utilization of staff. So we want to be more flexible in how we use our staff, and so maybe there's this mismatch between where the illegal activity is happening and where our offices are, and so this is going to be better. Other things is, some of these areas are very remote and difficult to staff, and there might be agency problems as well as security concerns of these agents. There have been reports of agents being killed, and this agency problem between, oh, you're my friend, I'm not going to fine you, might be a problem. And so having this decentralized system might actually be better at generating enforcement. All right, so we have a lot of data. The first data that we explore is this data from IBEMA on the organization and personnel. So we obtained the list of all the offices, where they're located, and from payroll data and worker trips data, we're able to see, assign both workers to offices and then also look at the deployment. So we are able to track workers on these deployment trips. We have data on satellite alerts at the month level, and then we combine that with fines data, where we know the coordinates and the exact date, which we can use, then match them to the satellite alerts so that we can see which satellite alerts ended up resulting in a fine. And we use a machine learning classifier to classify fines into several categories, so from deforestation, logging, biodiversity, and others. And then we also have data on land use, but I won't be showing you any results on that today. And we then aggregate all this into a pixel panel for the legal Amazon. So overall, what does our data look like? We basically have in orange the offices. The blue dots are where agents are deployed. So the trips, and then for the deter alerts, we can look at what their probability of a fine is, conditional on an alert. So let me start by telling you about what happens to agent presence once these offices close. So to do that, let me first tell you about how we define the timing of an office closing. So we focus on the legal Amazon, and it has, at the start of our sample, 50 offices, 50 field offices. And we define an office as closed as the first year in which it's staffed for less than 6 months with a permanent agent. And so we see that there's a staggered kind of office closure over time. The treatment is if the office is closed, and then our control group will be offices that always remain open, so the never closed offices. We're going to do identification strategy is going to be a difference design with staggered adoption. And yeah, won't spend too much time on this because not that complicated. So you might be asking, which offices did they close? And so here we're comparing offices that remain open to those that remain closed. And we see that, maybe not surprisingly, the ones that closed were smaller offices located in smaller towns that were more rural and were poor. And so maybe they did close the ones that are harder to staff, which is consistent with the story that they had. And they also seem to be less active in terms of fine issuing at the start of the period. So we see that kind of mechanically, there was a really large decline in whether the office had a permanent staff in that year. And interestingly, we also see that there was a decrease in the likelihood that you had a deployment in that year for the first couple of years. And so it's not that, now that there's less permanent staff at these offices, they substituted with more mobile deployment. They were not able to do that substitution of time. And this resulted overall in closed offices seeing a reduction in months with any agent present by 85%. So this was a really large shock to local enforcement capacity. Now, did this reduction in local enforcement capacity actually reduce enforcement in itself? Before going into that, let me have a little bit of discussion on, what do we expect to find. So if you think about the decision to deforest a piece of land, the agent's gonna compare the expected returns to the perceived cost of land clearing. And so the returns are not changing as a result of this policy. And so the question we need to ask is, how is the closure of offices impacting the perceived cost of land clearing? Well, the perceived cost is really the probability that you are fined. And we can break that up into two separate parts, one that depends on satellite detection and then one on ground detection. So local office closure is both changing perhaps the probability that you're fined conditional on satellite detection. It's also probably changing the probability of detection on the ground because you have less local knowledge of what's happening. And then at the same time, you might maybe think that the office closures are going to change the probability that you find conditional on local knowledge. So these are the three things that we need to estimate. We don't have any, perhaps, probability of satellite detection is not impacted by office closures because that is an independent function. Today, I'm going to focus on the first object, which is thinking about how the probability of fine changes conditional on satellite detection. To do that, the identification strategy is going to be to create buffers around offices, thinking about, this is going to be the area that they have, control over. So this is the area where the enforcement happens. And, so for each office, we create a buffer around it. And for example, some pixels will be around buffers of offices that closed and opened. If you're around, so we only count you as treated once all of the offices around have closed. Again, we're going to do the same regression, but now at the alert level. So the outcome variable that we're going to be looking at is the probability that an alert receives a fine. What we find is that there's an overall decline in the probability that an alert is enforced on by 31%. And then we can break that up into timings, so and land tenure. So remember that on public land, it might be harder to identify who was responsible for that alert, while on private land, you're able to link the alert to an owner. We see that the decline is driven by fines given on primarily public land by 42%, which is what is expected. We can see here that there's a really large decline actually in this local knowledge, because we're able to tell whether a place that that is going to receive an alert, whether it is fined ahead of time. And we see that there is a decline in this preemptive and anticipatory enforcement. For both private and public land, we see that there's a decline in kind of quick actions, so the probability that you're fined within the first 2 months of the alert. And very interestingly, on private land, there's just a delay. So there's a shift between the probability that you're fined between months 0 and 2, but then there's an increase that you're fined later on. But on public land, that probability continues to decline. And so this really seems to be linked to this ability to identify offenders on private land, but not on public land. So those are all the results that we have for today. So these preliminary results are showing that these field office closures really did have an impact on enforcement presence. And that resulted in a change in response to satellite alerts, both in reducing anticipatory enforcement, but also on private land, response is simply delayed, while on public land, enforcement is reduced forever. The next steps is to think about how these changes in enforcement are affecting deforestation and estimating the other parts of the probability of fine to be able to put everything together. Thank you so much. Looking forward to your comments.
Thanks a lot. Open for questions, comments.
Very nice paper, very nice presentation. So my first question is, so what is exactly the treatment? Is it 0-1, so either the office closed or didn't close, or around the area, or do you have a continuous measure of how many offices closed or how many people were there in those offices? That's the first one. And then the second one, I'm trying to think about this result, about why the probability of alerts that receive a fine goes down. Could it be that this technology of remote sensing is an imperfect one, so there's more false alarms, so when they actually go there to check, it turns out that it wasn't really a real case, so that's why they don't assign a fine.
Let's collect a couple questions, yes.
Thanks, super interesting work. Is there any difference that we should be thinking about in terms of compliance with these fines based on how the fine was levied? Like, there's been cases in the US about running red lights with traffic camera, and people are more able to fight those, or they're more willing to ignore those kinds of fines versus ones that are levied by a police officer in person, and should we be thinking about that as a dimension as well?
We have one last question.
Yeah, it's also related to how do you define well, not the treatment effect, but rather the control group. So you were saying that your control group is never treated offices, but then you, on your discussion, you also mentioned that treated or closed offices look very different to always open ones, and that might, even if you are going to have some controls, you may think that those that close are fundamentally different, maybe in some unobservable trends, and hence maybe you should, or maybe try just simply exploit the timing of the event among the group that received the treatment, rather and sort of exclude the never treated.
Thanks so much. These are all great questions. So on the first one, yes, currently we are defining treatment as either your nearby office was closed or not, but I think there's more that we can do in exploring the distance to offices in a more continuous way, and that's definitely one of the next steps that we're going to have. And I guess that relates to your point of, like, is the never treated group a good control group? I think we need to do a little bit more in trying to justify whether that is, and explore whether the treatment timing is also correlated with characteristics of offices and all of that. So these are definitely things that we're thinking about moving forward. We do see that there are pretty parallel trends in outcomes. So, you know, differences in levels are not necessarily a problem, but definitely selection into treatment might be. And so I think we need to do more in thinking about that and doing some more robustness checks with different either different definitions of treatments, so using the continuous variables, and also using the not yet treated only as controls. Problem is we do have only like 30 offices that close, so sometimes that gets a bit tricky, but we will definitely do more on that. Then on the probability that you receive a fine conditional alert, whether that can be driven by false positives. So I think for sure there are false positives, but when we actually look at enforcement by size, the enforcement is mainly for really large deforestation events where they're pretty confident that the event happened, and also that the person might end up paying the fine or so on. And so I think that these results would not really be driven by that, but we can do more to explore that false positive. It's kind of difficult to know like what is the ground truth because the satellite data on forest cover also has measurement error, and yeah, so we've been doing a lot of work in trying to think about that. But I do not think that false positives would be driving this. I think it's more really this delay, because for the private places we do see enforcement doesn't change that much. It's mainly the delay in timing. So it might be more linked to this new operational capacity that you're not there on the ground to respond. You need to organize a trip. You need to, and also, those might not be the priority areas. And so thinking about how this is changing enforcement across other places is also something that we will think about next. And then on your question on whether there's differences in compliance based on how fines are levied, that's a really interesting point that I had not thought about before. And I think it is especially important because actually a very small portion of these fines are ever paid. And so thinking about like the deterrence effect of agent present on the ground, I think is really interesting. And yeah, we'll think more about it. Thanks so much.
Thank you. There are no further questions. I see you have one more.
So you talked about selection into treatment, but because you're exploiting the staggered rollout, could there be selection to the timing of treatment? So who gets treated first?
Yeah, so that's what we need to think about as well, right? If these offices were being closed down because they were impossible to staff and the more remote ones are harder to staff, there might be some unobserved, or we could maybe try to measure that and look at how that happens. And I think that's actually important because I didn't talk about this today, but actually there was a law that mandated the closure of these offices in 2016 and 2017. But then when we looked at the data, a bunch of these offices were already kind of unstaffed before that. And so you might think that really they're just closing the ones where they're not able to find people that are willing to go there. And so I think that's definitely an important thing that we need to think about. Thanks.
Thanks a lot. So we go to the last paper of this session, but we stay within the same space of detecting environmental damage and how to enforce it, in this case from India. This is a paper by Aditya Dasgupta from the University of California, Merced. Aditya, the floor is yours.
Hello, thanks for hosting me remotely. Okay, so my slides are up, I see. I guess is there someone on that end who will change the slides? Or
yes.
Oh, okay, I'll share the slides. Okay, here. Okay. Okay, so you should be able to see this, I think. All right, so let me get started. So this is a paper which looks at the impact of a initiative to use satellites to detect stubble burning in India, and looks at some unintended consequences in terms of farmers in India learning how to game the satellite technology. So just by way of context, North India is one of the world's most polluted airsheds. And a major driver of this air pollution is post-harvest stubble burning of rice paddy in the wintertime. particularly in the agricultural state of Punjab, which heavily subsidizes rice cultivation. The government in Punjab has technically, rice burning is illegal, but the Punjab government has historically not enforced laws against burning because farmers are a really politically powerful constituency in the state. And this is amplified by pollution externality dynamics. Okay. So here's a picture of detected fire points in the Indian state of Punjab, overlaid with a depiction of smoke, which tends to travel in the winter from Punjab to nearby cities like Delhi. Okay? So despite all the negative externalities for Delhi, right, these aren't internalized by the Punjab government. And so it doesn't really do a lot to enforce laws against burning. Yeah. Why do farmers burn? This is essentially the fastest way to get rid of the leftover straw after harvesting rice and the wheat, to make way quickly for planting wheat in the spring. Yeah. So if anyone has been to Delhi in the winter, you'll know that Delhi has some of the worst levels of air pollution in the world, with AQI levels which are routinely on average around 300. Every day, and so it's becoming an increasingly salient political issue. Yeah. So I basically study the effects of a shock to political will to crack down on burning, arising from cross-border political alignment. Okay. So in 2022, for the first time in history, the party governing Delhi, which receives all this farm fire smoke, came into power in the state of Punjab, which produces it in elections. Okay, and consistent with what you might expect theoretically, they actually start to try and crack down on farm fires to deal with these pollution externalities. In particular, they start to use satellite monitoring of fire points to detect fires and send bureaucrats down to villages to basically issue fines to where fires have been detected. And according to the satellite data, this campaign appeared to be incredibly effective. In 2024, detected fires fell to their lowest levels in recorded history. Yet mysteriously, air pollution in Delhi remained the same. Okay, so this is a bit of an environmental whodunit mystery, and you can see this in this plot here. So what this shows you is in yellow and blue, right, in the winter time, these are detected fires in Punjab, okay, according to MODIS and VIIRS sensors. Okay, and the dashed line represents average PM 2.5 levels, a measure of air quality, at the US Embassy in Delhi. Okay, and you'll notice that generally speaking in the winter, the two move together. Okay, but after 2022, fires that are detected steadily go to increasingly low levels. They were lowest ever in the winter of 2024. Yet the smoke levels in Delhi remain as high as ever. Kind of posing a mystery, what happened here. Okay, and my argument in this paper is that basically farmers learned how to game the satellites. Okay, so I'm going to use a difference in discontinuities design at the boundary of Punjab with neighboring states and neighboring Pakistan, and I'll show that using the spatial discontinuity design, detected fires did in fact plummet right after the policy was implemented. But I also provide evidence that most of this drop was actually driven by farmers shifting burn times to evade the times at which satellites basically pass over North India. The way in which I estimate hidden fires is basically by using a machine learning algorithm to impute the true number of fires from burn scars, which cannot be concealed. So after a farmer sets a fire, it leaves a signature on the ground that persists and can't be hidden from satellites. So using this approach, I'm going to show that basically about 80% of the apparent drop was driven by evasion. Okay. So, how do I interpret this? Basically, I'll provide evidence that what likely happened is that local officials basically colluded with farmers to game the monitoring technology as a way to kind of meet enforcement metrics while avoiding the social costs of enforcing against farmers locally. And I think the broader lesson is going to be that it's quite appealing to just try and use new technologies to monitor and enforce against things we don't like. But there are limits to this approach when you fail to address root causes or incentives that underpin the behavior of concern. Okay. So let me give you a little bit of background on satellite fire detection in India. This technology has existed loosely in India since 2018. India's space agencies and state-level remote sensing centers have used NASA's MODIS and VIRS satellites to basically thermally detect fire points in North India to kind of monitor the extent of stubble burning. Both MODIS and VIRS satellites are polar orbiting satellites, which means that they have high spatial resolution, but their overpass over North India is intermittent. Between the two different satellites, they basically have coverage between 10:30 a.m. and roughly 2 p.m. in North India. But until 2022, this data was only loosely used for analyzing trends and maybe very loosely guiding enforcement policy. This changed in 2022 when the Aam Aadmi Party, the party governing Delhi, came into power in Punjab in elections. And what they did is they implemented a new policy that tightly linked enforcement to Firepoint data. So they created an action plan that explicitly aimed to meet a 50% reduction in detected fires in each district relative to a baseline prior to the policy. And between October 15th and November 30th of each year, the Punjab Remote Sensing Center basically took every detected fire point that comes from these NASA satellites, sent it by text message to a designated village official to basically investigate the fire and file an action taken report within 24 hours with a picture of the field and an indication of what action was taken, including whether fines were given. Okay. This data was then collected centrally by an agency called the Punjab Pollution Control Board, which basically coordinated kind of like overall progress with district level heads to basically assess whether districts were on track to hit this 50% reduction target. So this is a bit of a schematic of what the procedure looked like. The NASA satellites basically detect fires in North India between 10:30 a.m. and 1:30 p.m. Every day. India's space agency gets real-time access to this data from NASA. And by 4:30 p.m. every day, it sends the detected fire points to the Punjab Remote Sensing Center. PRSC then sends a text message to a designated official in each village whenever a fire point has been detected in a village's polygon. And that village official then has to upload an action taken report to this online system. And then the Punjab Pollution Control Board is basically monitoring overall district level statistics on fires detected and whether actions have been taken and fines have been distributed. Okay. So this is a map of grid cells in North India. This is Punjab. These are the 3 neighboring states in India, and this is neighboring Pakistan. And this is just showing you changes in detected fires per grid cell from the pre-period, which is 2020 and 2021, to the 2 post periods, 2023 and 2024. And just visually, you can see, right, that there's this huge reduction in detected fires within the Indian state of Punjab, okay, according to the VIRS satellite. And so this is something that the AAP party in Punjab immediately took credit for. They tweeted out, this 94% reduction in fallen farm fires and kind of advertised politically, all the steps they took to achieve this, including strict monitoring using satellites. Okay. All seems good and well on the surface, but I think we need to be sensitive to Goodhart's law when it comes to environmental governance. Goodhart's law basically states that when a measure becomes a target, it ceases to be a good measure because when you start monitoring using a particular measurement technology, you're also incentivizing people to try and game that technology. Okay. And in this context, there have been rumors, right, that farmers have basically, this wasn't a real drop in burning, but really driven by farmers shifting burn times to the evening to invade the satellite overpass times in the late morning and early afternoon. Okay? This is quite plausible in this context because qualitative fieldwork I've done suggests that when village officials actually go out to the fields to try and enforce and distribute fines, they basically face a lot of social backlash from farmers. And so gaming could be a way for these local officials to kind of ease enforcement pressure while avoiding the social costs of actually issuing fines against farmers. Okay. So empirically, what I do is I create a grid cell level data set of satellite detected fires in North India. The first set of analyses is with regards to detected fires, and the dependent variable is change in, sorry, there's an error here. It should be average fires detected per 100 square miles from the pre-period to the post-period, so it's a measure of change. Treatment is an indicator for the Punjab side of the boundary in a spatial RD framework. And the running variable is going to be distance to the border with segment-specific fixed effects and flexible slopes that are allowed to vary on each side of each segment boundary. And using a 100-kilometer bandwidth, so we're only using a 100-kilometer selection of grid cells along the Punjab boundary with its neighboring jurisdictions. Okay. So this is just what the spatial RD results look like in raw form. On the left is MODIS data. It has lower resolution, so you pick up fewer fires, and on the right is VIIRS, which has higher resolution, so you pick up more. But you can just see right here that just outside of Punjab, there's no real change in detected fires over this time period. As soon as you cross into the Punjab side of the boundary, there's this huge negative change, this huge reduction in detected fires by about 70 fewer farm fires per 100 square kilometers, according to the VIIRS data. Okay. So we can look at the regression tables for these RD results, and you basically, pooling across the full sample here tells you that we estimate that after the policy took effect, you saw about 70 fewer detected fires per 100 square kilometers in Punjab, relative to grid cells just across the boundary in neighboring jurisdictions, both in India and in Pakistan. This was overwhelmingly concentrated in the winter when this policy goes into effect, right? When the satellite monitoring is happening. And this is also when most of the farm fire smoke is affecting Delhi. You don't really get the same kind of effect in the spring when it's not a salient. Okay. Okay, so the really interesting part is estimating hidden fires, okay? So the way I estimate hidden fires is basically use the pre-2018 data before satellites were ever used for any kind of fire monitoring. And I train a machine learning algorithm to predict true fires from burn scars, which is basically based on MODIS satellite imagery. There are existing products which basically measure at the pixel level. In a given month, is there evidence that this pixel was burned, okay? So for a grid cell, I have the burned area image, and then I also have the image of detected fire points. And I have close to 1 million, training examples. I train a computer vision algorithm to basically take the image of burn scars and try to predict what was the true number of fire points, okay? And then I basically compute hidden fires by using the algorithm to predict the true number of fires and subtract from that the number of fires that was actually detected. This is a really simplified version of the kind of computer vision algorithm that I used. Basically, as input, it takes 2 images, one of which is a grid cell kind of raster file or image of like burned pixels. So these are the little points here in white against black. Sometimes pixels are obscured due to cloud cover, so we include another image of whether or not the pixel was visible, depending on cloud cover. And I use those 2 to basically predict a blurred or an image that has fire point data that is then smoothed with a Gaussian blur. Okay, and basically we give the computer vision algorithm hundreds of thousands, close to 1 million examples, and let the algorithm learn how to map burned area to true number of fire points. Okay, and we integrate over the raster, the predicted raster, to compute what was the true number of fires in this grid cell. Okay. So let me show how this algorithm does out of sample. Looking in the left panel in the pre-period before this policy went into effect in Punjab. And we can see that predicted fires based on burned area imagery is really good at predicting the true number or detected fires in the pre-period. It's almost perfect one-to-one slope, and you can explain, over 80% of the variation just based on burned area. After the satellite monitoring policy goes into effect, you can see that this relationship really collapses. And in particular, for a given level of predicted fires from burned area imagery, all of a sudden the number that are actually being detected by VIIRS and MODIS sensors are quite below the one-to-one line, okay? Implying a large number of hidden fires, okay? So we can then do a spatial RD where the dependent variable is not now detected fires, but hidden fires. And here we see that basically as soon as you cross into the Punjab boundary, you have this huge jump in the number of hidden fires. On the left is MODIS data, and on the right is VIIRS data. Yeah. So here we can do the same kind of like regression analyses of the impact of this policy going into effect on the change in the number of hidden fires, comparing Punjab grid cells to grid cells just across the boundary. And what we can see is that basically after this policy goes into effect, there's this huge jump in the number of hidden fires, close to 60 additional hidden fires per 100 square kilometers. If you compare this to the change in the number of detected fires, what it implies is that about 80% of the observed reduction in farm fires was actually driven by farmers shifting burn times to the late evening. I'll just gesture at some other analyses I've done. One of the things we're looking at is the spatial diffusion of hidden fires over time in Punjab. So these are grid cells in Punjab comparing to a baseline in 2020. So in 2021, relative to 2020, there's no real change in hidden fires. Again, this is pre-policy going into effect. But as soon as AAP comes into power in 2022, you see this huge surge in hidden fires, okay, concentrated in this part of Punjab, okay? And that more or less persists over the next 2 years. What's particularly interesting here is it's not a story of slow contagion, okay, or decentralized polluter learning. Instead, what appears to be the case is that as soon as Punjab starts to use satellites for detecting fires, almost immediately all over the state, farmers learn how to shift their burn times to evade detection. Okay. So, my interpretation of that is that this is probably not likely to be a storyline about just purely decentralized polluter learning, but instead, basically some degree of collusion between local officials and farmers to kind of game the new monitoring technology. Some other analyses we do is we show that the underlying kind of crop cultivation patterns driving rice burning didn't really change much after this policy was announced. You still see lots of wintertime rice cultivation, and you still see lots of associated burning. So the underlying fundamentals didn't change after this policy went into effect. In ongoing work, we have a lot of data on the identity of the village officials who are tasked with enforcement, and we want to look at whether officials who are more socially embedded and vulnerable to social pressure from farmers were more likely to engage in this kind of fire hiding behavior. So just to conclude, new technologies and sensor data offer the promise of improving environmental enforcement. But I think if you don't pair that with addressing root causes and underlying incentives, this can result in perverse incentives that basically cause officials to just hide rather than fight fires. And in the Indian context, what happened is satellite monitoring didn't address the fundamental need to basically eliminate the subsidies which encourage farmers to grow rice in the winter. And I think maybe a broader lesson for the literature in remote sensing and environmental governance is Goodhart's law. We need to be careful about using as measures for policy evaluation the same kind of metrics that are used to guide policy. Because as soon as you use it to guide policy, polluters are going to start to learn how to game that measure. Okay, so I'll stop Thank you so much.
Thanks a lot. Lots of action with satellites and use and abuse. Opening for questions, yes.
Yeah, to my knowledge, the air pollution due to burnt rice straw is serious only in Delhi in this world. So it's very special. And then you explained that the smoke comes from Punjab. Punjab is a very, very special place again. Farms are very large, farmers are very rich, and the large machines are being operated. And some of the farmers own the second houses in Canada, and they go to Canada when it's very hot in India. So I think I may not be right, but it has something to do with political power of the large farmers. So if you have data on farm size or political connections, I think it becomes very clear. Because only in India, it's a shame for Indians to have air pollution all the time for the last 20 years or so.
Thanks so much. Great presentation. I was wondering if your story is, they shift the timing that they are doing the fire, but the other possibility which you were also talking about is the cloud cover, right? And so are you able to tell whether they know how to game because of the timing, or if they just choose to burn on different days? I don't know if that's something that you can look at in the data or anecdotally. Thanks.
Yeah, you were saying that there's no spatial contagion, so that all around Punjab you see these hidden fires. Then I'm curious, like, what do you think that explains the slope you get in the not RDD, I mean, I think you get what I'm saying. Like, you were showing that the farther you go from the discontinuity towards the Punjab side, the less or the more fires fall, the more detected fires fall.
Mm-hmm.
Thank you so much. That was so interesting to hear about. I just had a question about how you think the farmers learned so fast how to game the satellites, since the change was already seen in 2022 and the policy was implemented. I know that would be an assumption, so I was wondering what you thought. Thank you.
Mm-hmm.
Okay, thanks a lot. Back to you.
Yes, so thank you for those terrific questions. On the first question about the political power of farmers, I think that's very central, and so I think in particular, why it's so hard for these village officials to actually enforce the law against these farmers is I went and did some field work in India, and basically what you hear is they go out to the fields to they get an SMS that a fire point was detected. They go out into the fields to issue a fine, and what ends up happening is the farmers gather and start heckling the official, and many of these officials actually live in these villages. They're very local officials, and so the power of farmers politically and socially is partly what makes enforcement really difficult. And so I agree. It would be interesting to try and measure the social and political power of farmers, maybe via land holdings or other data. So that's a great suggestion. Thank you. The second question on are there other ways to game the satellites, like using cloud cover? That's an interesting thought. That's not something I'd considered. From my just like qualitative interviews, what I understood is it started to become common knowledge that like the satellites overpass at these times, and so we can evade them quite easily by switching burning to the night. But I do wonder, I mean, maybe they also exploit cloudy days. This is of course in the winter when you know it's far away from the monsoon, so you don't have that much cloud cover. You do have smoky days, but the sensors on MODIS and VIIRS are actually able to detect fire points thermally, even when it's smoky. But that's something I'll look into. On the third question about spatial contagion and what explains the slope in the RD plots, so the RD plots can be a little bit misleading in the sense that they pool across all four boundaries, okay, in a kind of, you know, in a kind of Frankenstein average way. The regressions don't do that. They use boundary specific fixed effects and flexible slopes on each side of each boundary. So I think what you see in those kind of like slopes in the RD plots is partly a function of weird averaging across different boundaries. But it's also a function of the fact that not all parts of Punjab are suited for growing rice. And so as you move away from the rice growing areas, you just have less baseline kind of like burning in the winter. So I think it might be picking up some of that. And on the fourth question, how did the farmers learn so fast how to game the satellites? I think that's a terrific question. It came as a surprise to me because I actually expected to see some kind of like slow learning, you know, like one village starts to do it and then you start to see farmers in neighboring areas start to do it. But essentially what happens is in the very first winter after this policy is announced, immediate hiding of fires all across the state. And my interpretation is basically the incentive structure looked quite similar across the entire state. You're asking these village officials to, for the first time in 20 years, go out and start distributing fines to this extremely powerful social group. They're just not going to do it. They don't have the capacity to do it. And so you have fairly uniform incentives across the state to game the system to hide fires rather than fight fires. So thank you for all the questions.
Thanks a lot, Aditya. I think with this other fascinating presentation, we can close the session. I think it's closed at 4. So thanks a lot for very fascinating presentations and your questions and the presenters. So